Hybrid UAVs combine advantages of multi-copters and fixed-wing planes. A typical hybrid UAV can switch between copter and plane modes. The copter mode gives the hybrid UAV more maneuverability, while the plane mode is more efficient in long-distance flights. Controlling a hybrid UAV, however, is very challenging due to the complexity of the dynamics when both rotors and wings are active. Traditionally, people design hybrid UAVs controllers manually. The controller design process is highly specific to the dynamic model of each UAV, and the design knowledge cannot easily be shared. In this paper, we propose an automatic way to design the controller for various hybrid UAVs using reinforcement learning. The first step is geometry design. We build a dataset of parameterized components for hybrid UAV designs. Users can create new vehicles by mixing and matching parts from this collection. This allows us to create vastly different configurations of hybrid UAVs. Once we have a design, we train a neural network controller using reinforcement learning. To narrow the reality gap, we propose a novel reward function and new integral block in the neural network controller. Here we show the controller after training for 25, 50, 100, and 400 iterations. Without any knowledge of the specific flight modes and the transition state, it manages to learn a functional velocity tracking controller after 400 iterations. The controller allows for a smooth transition from loitering to advancing. Next, we show our quadplane following a triangular trajectory using our trained neural network controllers. In this example, a tail sitter is instructed to track a time-varying target velocity as closely as possible. Here, the X-wing model is doing an autonomous flight by tracking a pre-programmed target velocity that forms a circle. Finally, the double-wing model is flying along an S-shaped trajectory to avoid obstacles. The simulation experiments show that our model-agnostic method is able to generate controllers for wildly different configurations of hybrid UAVs. This video shows the ablation test with two key components of our pipeline, showing how they dramatically lengthen the flight time and decrease the velocity tracking error. Once we trained the controller, we deployed it on hardware to verify its robustness. Because of the reality gap, a naive controller without our proposed modifications crashes catastrophically when implemented in real hardware. After incorporating the integral block and orientation cost proposed in our work, our trained controller was capable of finishing the flight task successfully. Our controller design generalizes to hybrid UAVs with significantly different dynamics. For example, in order to enter gliding mode after hovering, the quadplane controller simply redistributes thrust between front and other rotors without needing to change its orientation too much, while the X-wing has to lean forward by a lot to transition from copter mode to gliding mode. When this quadplane is hovering, it can be seen from the log that all 5 rotors are actively being used. However, when the quadplane enters gliding mode, we can infer from the large margin between the weight and the net thrust that the wings contributed some lift to balance the weight. Thank you for watching.